So, and our administration also restricted the movement of students, so they cannot go out of hostel. Only the very few students, let's say per department, 10 PhD students can go to lab.
Okay.
So it is very difficult situation. Even I am also a warden, so we need to go to visit the hostels and see. But anyways, yeah, most of the students they are responsible, but some of them are very young. They are not matured, and that is the issue. I mean, they are not very careful a lot about this.
So students are still in the hostel?
Yes. We have more than, I think, 3,000 students now here in hostels. Total number of students we have, like more than our full strength is more than 6,000. It is almost 7,000. But now we have probably more than 3,000 are there, and very soon we are actually sending our BTech students voluntarily. I mean, BTech students also, they came not first year, second year, third year, and fourth year. So we actually wanted to have offline classes for MTech and PhDs, not BTech, but that also we cancelled. And our administration is saying now even PhDs also can, if voluntarily they want to go home, they can go. But more importantly, we need to send the BTech students home because the cases are increasing even in Assam, and then we want to have like at least 2,000 or less than 2,000 students in campus, not more than that.
But obviously PG and PhD students, they will be there on the campus.
Yeah, only PhD, maybe MTech also, maybe second year, because yeah, MTech students, some maybe some of them will be who are working on projects second year, they will be here.
Yeah, they will be on the campus, but obviously, yes, they have to work in laboratories.
Yeah, but it is voluntary. Whoever wants to go home, and that doesn't matter whether they have experimental work or whatever. If they want to go home, they can go.
Correct. So it is up to them. If they feel they are not secure, they can leave.
Yes.
Yeah, that is true. Very good. That is true.
Yeah,
So
but
we
now,
wish, even
yes.
after this pandemic, we wish to exchange few of our students at the Guwahati, so they can work under your able guidance for certain project for a month or 1.5 month, or for a full semester project work also they can work if it is
Yes.
possible at the IIT Guwahati, because
Yes.
that will give the best exposure to our students.
Yes. Yeah. Anyways, we take summer interns or winter interns also sometimes. But only thing is, IIT Guwahati, anyways, this internship generally, I don't know, maybe some professors may have some different fund, but generally we don't give a stipend for internship. Like some other IITs, they have some selected students, they give stipends also. I know Kanpur, Madras. But we don't have that kind of stipends. Once institute wanted to decide something on that for few selected students, but now it got cancelled, I think.
That depends. If you have project funding, if it is available, then only you can give. But the most important part is that student can get best exposure. They will get the exposure of working with IIT in the laboratory under the experts. That is the more important part.
Yes, we get a lot of students from across the country. So many colleges, even IITs, NITs also, some students we get.
Okay.
But yeah, this is good. I think the students also want to visit this part of the country. So,
am I audible, sir?
100%.
Thank you so much. Good afternoon, everyone. Thank you for taking time out and being here today for a webinar based on metal 3D printing and 3D printing mechanical metamaterials. I, Chandana, welcome you all on behalf of Chemical and Biochemical Department, Indrashil University. I'll begin the event with introducing the panelists. We have Dr. J.S. Yadav, Dr. Amish Vyas, Dr. Arun Kumar, Dr. Sumit Chaudhary, Dr. Siddheshwar, and a very young and dynamic speaker, Dr. Prasenjit Khanikar, a mechanical engineer from professor from a mechanical engineering background, IIT Guwahati, an alumni of North Carolina State University, and an IIT alumni from. Now, I would like to say that we are very fortunate to have you with us, sir. Let us introduce Dr. J.S. Yadav, a retired director from IICT. He is presently associated with Indrashil University as Provost, Director, Research and Trustee. He is a recipient of India's most prestigious scientific award, Shanti Swarup Bhatnagar Award, and many more national and international awards for his valuable contribution in the scientific world. So I would like to request Dr. J.S. Yadav for opening remarks.
Prasenjit, oh, okay. Now I can. So how are you? So,
Yeah, I'm good, sir. I'm good.
You are good. So,
Yeah.
So
So it's
we-
our institute. Yeah, our institute is having a difficult time, but still, yeah, we are still okay. Yeah.
you know that that area, a lot of people have, they look for some opportunity to write something. Otherwise, situation is not that bad, Miss, I would say.
Yeah, no, but now I think in campus we have a lot of COVID cases.
Right.
Yeah. So.
Actually, I was supposed to come in February 5th, 6th, something,
Oh, okay.
that meeting, but it has been postponed.
Oh, okay.
At Chemical Research Society of India meeting.
Okay.
So they have given me, you call it gold medal, lifetime achievement award, something.
Oh, okay. Oh, good to know, sir.
They give only to the people who are above 70. So I was supposed to come and speak.
Oh, okay.
You know Punyamurthy, right?
Yes.
He was organizing.
Oh, okay.
And a lot of people are supposed to come. Anyway.
Yes.
The thing is that I like to welcome you for our university, that you have agreed to give a seminar. And most important, very important topic, metal 3D printing and 3D printed mechanical metamaterials. You know, I was in a committee where I think Venugopal Rao also worked on the 3D printing, right? Was a director of IIT Delhi.
Yes, I'm not very sure actually. Yeah. I mean,
Somebody from IIT Bombay
Uh-huh.
award, Nasi Reliance Award. So they, at that time I reviewed the work. I maybe some, I thought it was Venugopal Rao only, somebody.
Okay. Sir, actually, although I'll tell you that I'm not an actually kind of direct 3D printing guy. I'm more on the material side only. Yeah.
Okay.
So I'll yeah.
So that is more important, no? You have to make material, right?
Yes, sir.
So that is more important, no?
Yes.
And especially our people have chemistry group is strong, chemical engineering is very strong. So, and of course, mechanical engineering somehow our last couple of years, some problem to get a student. The same problem is everywhere, or only in Gujarat this problem is there. So,
No, sir, we have problem. Yes, mechanical.
So maybe your lecture, because it is open to so many, I don't know. Your lecture, YouTube and everywhere there, probably may help people to take admission in mechanical engineering. Only thing is that I request you to present in such a way that they should, I'm sure you are already prepared, but present in such a way, they should think that doing mechanical engineering is going to help more in the career rather than, taking other subject. Like, when we talk, whatever you talk, Sumit is there, he may get offended. You talk computer or whatever you talk, computer engineering, computer science, or whatever you talk, machine learning they talk, AI they talk. Do you think they can do without material and without mechanical engineering?
No, sir.
No. That part you have to tell. If they can just sitting on the table, develop the software. Mechanical engineer is the one who develops the programming. make the machine learning going, robotic, whatever you call it, is the mechanical engineer who makes it reality.
Yes, yes.
Is it true or not?
Yes, sir.
It's true.
Yes. What, Sumit, you said no or yes?
Yes, sir. Yes, sir.
Yes, sir. Yes.
Even
Because without mechanical engineering, your computer is useless. Mechanical engineering and material.
Yes,
Okay.
yes.
One thing. Second, also I can tell you, you talk about pollution, this, that. Computer making creates more pollution than anything else industry, by the way. Maximum pollution. And without knowing, you people keep on telling pollution. And the material, what goes into your computer, is all made through mechanical engineering and chemistry. I don't know whether you know it. It's a very important area. And what we take in 3D material, which is needed, today is all material. Biomechanics, Metatronic is all part of mechanical engineering, which is, I don't know how many things are fixed in people's body, which comes from the mechanical engineering material. You can make artificial heart, you can make artificial limb, you can make now the knee replacement and all those things. It's all mechanical things coming. They are very important. So I said it, but I'm saying, Prasenjit, you work in that area. If you project, so let the student watching on YouTube or Facebook or all this. So that taking mechanical engineering is a good.
Yes, yes, yes.
And Dr. Bajaj's son is a mechanical engineer. Son is a mechanical engineer from IIT Madras. But they are doing very well. So it is not what you call it. It is the subject which is the mother of all engineering. Okay, we say chemistry is central of all sciences. Mechanical engineering, mother of all engineering. Is it true or not?
Yes, sir. Yes.
True, sir. True.
That's it. So with this keyword, I'd like to request you to go ahead, proceed with the function.
Thank you so much, sir. You have already given the enough boost for the mechanical engineering. Thank you for that.
No, but it is no exaggeration. Ask Prasenjit.
Yeah, indeed. I agree to it, sir. I agree.
Agree, okay.
Yeah. So this is to inform to all the participants that there would be a chat box enabled for Q&A session, which would be conducted at the end of the session. So here is a golden opportunity for all of you to just put down all the questions to ask our Dr. Prasenjit. Now, I would like to request Dr. Amish Vyas, Dean of School of Engineering and Registrar of Indrashil University, to introduce the key speaker.
Thank you, Anna. And special thanks to Dr. J.S. Yadav sir for setting the content for this webinar. It is very important webinar, and we rightly Dr. Yadav sir has said it is the mother of all engineering, because see, without material, nothing has been possible in this materialistic world. So in that case, I would like to say this metal 3D printing and 3D printed mechanical metamaterials, these are the very relevant topic for this generation of the mechanical engineers. And we have a very correct and right person for this kind of the topic, Dr. Prasenjit Khanikar. He is an assistant professor in the Department of Mechanical Engineering at IIT Guwahati. He works in the field of 3D printed mechanical metamaterials, high entropy alloys, and the high strain rate behavior of materials. His research interests also include the metallurgy of metal 3D printing. Before joining IIT Guwahati, he worked as a postdoctoral research scientist at Columbia University, New York City. He received his PhD in mechanical engineering from the North Carolina State University. He is an alumnus of IIT Delhi, and he received his MTech in 2008 from the Department of Applied Mechanics, IIT Delhi. He received his BE in mechanical engineering from Jorhat Engineering College, situated in Assam. And if you are aware of it, but this is the easternmost engineering college of the country for 5 decades. And from easternmost country to the western, and western to the Guwahati, and you can see the ladder of success for Mr. Dr. Prasenjit Khanikar. And today we are fortunate enough to have him with us for a very important topic related to 3D printing, and especially with the materials, metamaterials and mechanical metamaterials. So with this, I would like to welcome Dr. Prasenjit. Thank you very much for accepting our invitation, and welcome to the Indrashil University.
Yes, sir.
Thank you. So I can share the slides now, right? So,
Yes, sir, absolutely.
okay. Thank you. So let me. So is it visible now?
Yes, sir, it is.
Okay. So yeah, the very good afternoon to all of you, distinguished panelists and faculty, colleagues, and my dear students. So this is a great opportunity for me. I'm very happy and honored, as you know, from eastern most part of India to deliver something on in western most part of India. So sitting here, I'm delivering the lecture, so that is very I'm happy about it. And also thank you all the organizers, I mean, for inviting me. Special thanks to Dr. Siddesar Rautre for contacting me. So so this is my topic is I have a little bit expertise on mechanical metamaterials, so which is 3D printed. So I'll use my pen because maybe it is be better than pointed. So metal 3D printing is not my expertise actually. I have studied. We got a metal 3D printer recently last year, but it is not yet installed because of some pandemic condition. But my students, PhD students, have started working on literature and other research, the metallurgy of 3D printing. But why I kept it in the topic, because to know about mechanical metamaterials, probably we need to know a little bit of 3D printing as well. And 3D printing is mostly, I'm not so sure about your university, but mostly other students, students maybe probably have seen probably polymer 3D printers, not the metal 3D printers, because metal 3D printers is not available in many places. It is very costly also, and because metal needs very high temperature to melt. So so what I will do is I will start with metal 3D printing, very superficial. I will just tell you just few things, and then I will go to our research area, mechanical metamaterials, which is I'll show you. The metamaterials are some kind of materials which shows man-made materials, which shows very extraordinary mechanical behavior. So these are the applications of. Yeah, just give me a second. I can. Okay. I'm not very used to with this Zoom. So okay. So the application of additive manufacturing, all of us know that. So most of the structures probably you are seeing here are top 3 structures of metals. So it can be used anywhere. As you know, it's not only that. This is the most common probably picture you will see when you Google printing or metal 3D printing. Then the car engine parts, or maybe impeller in biomedical, and nowadays even the 3D concrete printing. People are making houses with 3D printing, and then also jewelries, and even food printing. And then very interesting field is the organ bioprinting. So there people are printing actually organs with that kind of biological materials. So I'm sure that all of you are aware of this. So I will just show, just to show you, different kind of metal 3D printings. So there are different kind of polymer 3D printers. So I'll just show you a video. Is the video is showing? I mean, I don't know, voice is not required, but video is going, right?
Yes, yes, indeed.
Okay. So this is one kind of 3D printing.
This nozzle can be mounted.
So I just keep it.
3D metal printer. The benefit of 3D metal printing is materials are apparent, whereby the high degree lower so. Furthermore, with this feature, you get the ability to use every metal powder which is available for 3D printing.
Sorry, this is one method that is called direct energy deposition or direct metal deposition, or also it is called powder nozzle based technique. So you have a laser. If you can see that light inside this, you have a laser, and then you have some powders coming from this nozzle, powders, metal powders. So that is one technique. But whatever printer we have in our department is the different one, because for some complicated shapes this doesn't work. But this is better for repairing work, I mean, as compared to the other technique. So if you have a let's say gear or something, that kind of part, and then you have broken part, then you want to repair it, this is a better technique. This technique, anyways, this slide is not very important, but again, they're showing the powder nozzles. So you have the nozzles here and you have the nozzles here. There can be more than one nozzles, and then you are building the part. But then another technique which we are more interested to study, because our metamaterials can be made by this technique, which is called selective laser melting, SLM technique, or it is called powder bed fusion. If you have notice that other one is called powder nozzle, because the powders comes from a nozzle, but here we have a powder bed. Where is the bed? So this is the bed, and you have actually powders. You cannot see these powders. I think that the very fine powders in micron level, let's say 50 micron, 30 micron powder size. So if you see this is again a video. So this is the laser. So after you do the laser work, I mean, then you will get the then you get the final product like this, that you can see. So yes, so this is what happens in this technique. This is called powder bed. As you can understand, there is a bed of powder. So this is the bed actually, like these are the powders, the red particles. So this is the product we are making, let's say for what we call metamaterials or whatever product, gear or whatever. So this bed, this is the bed, that bed will go down. And then after one scan of the laser, this is the laser pointer. So what will happen? The recoater mechanism. So after one scan, this like a wiper of our car, like this recoater will go and remove the extra layer of powder. So, but anyways, we don't want to discuss the mechanism much. But what I wanted to tell you, this selective laser melting or powder bed fusion is a better technique in terms of complexity of parts. Complexity, higher complexity can be achieved here. So there are different kind of classifications you will get in textbook. So this is one. This may not be the exhaustive one. There may be more techniques, but we are only focusing on metals. And then, as I told, we have SLM, or sometimes it is called SLS as well. So, and I have shown first DED, and then I have shown that is powder nozzle, and I have shown SLM, which is powder bed fusion. There is another technique which is also powder bed mostly, and then but they use electron beam rather than the laser. So this is another technique. So, but we are more interested because we have the printer in our IIT Guwahati. So we have the printer, although it is not installed, and also we can make the metamaterials with SLM. But EBM also can be used, but that is even a costlier machine, and there are some advantages in EBM. There are, I think, very few EBMs, electron beam melting machines in India. So I will go quickly. We don't need to understand all of them. I'll just go quickly. What are the process parameters in powder bed fusion? That is the technique we are interested in. So in powder bed fusion, these are some parameters. Let's say laser related parameters: the laser power, spot size, pulse duration, pulse frequency, and then how you scan it. How you scan to make the part. Scan means scanning by the laser. So that there are some parameters. What is the speed of scan? What is the spacing of scan? And how you are, what is the pattern? Like you are doing like this, or you are doing like, something like, let's say, little differently. You can do that kind of scanning as well. So those are very important. And then also that, what is the particle size, that powder size, or that kind of, what is the material properties of the powder, and then temperatures. These are the, why these are important. These are very, very important because these 3D printing companies took years to decide on these parameters. Let's say one very common material, SS316L, that is a stainless steel 316L, is the most common probably material for metal 3D printing. For that material, what let's say powder size, or what laser power, what scan strategy will be good. So these companies did research for maybe a few years to get a optimized value. So that is very important, because the new materials, if you want to do a new material which is not probably done by others, then you need probably years to find out optimized parameters. But now, as sir has pointed out, so that machine learning, I think some of you are, or many of you are from computer science. So that these people, they use machine learning, because sir has told, that's why I'm mentioning these things. So the machine learning is very important now in 3D printing, especially the when you have a 3D printer, you want to do you want to use a new material. And also these 3D printing companies, they now use machine learning. When they did not use machine learning, it took years to find these optimized parameters. What should be the powder size, what should be the laser power. But now they actually can do it at a very very low time, probably in a couple of months or maybe a few months, they can find the optimized parameter with the help of machine learning. Earlier it was not possible because they didn't use this technique. So now again I'm coming to this comparison of SLM and DD. SLM is the powder bed, that is the bed. I'll write bed here. And the other one is the nozzle. The first time I showed the nozzle one, where there is no powders on powders on bed. So now what important point is that you have more material flexibility in the other technique, not the nozzle technique. That means you can actually use different kind of materials. But here you have the material flexibility is not much. You have only special kind of materials. Let's say this is one common material, as I told, SS316L, this kind of stainless steel, titanium alloy, cobalt chromium, Inconel, Hest alloy, Merizing steel. So these are materials which are recently have been, companies have been optimized the parameters for these materials. But there are more materials are coming in, but not any. It is not like that you take any kind of material and put it in the 3D printer. You make some powder and put it in 3D printer. You will not get a good product. It will break easily, or it will it will have a lot of porosity. But then some materials, even it is for aluminum and copper, DD has some difficulty. We are not going into that. I mean, DD has some difficulty. It cannot print these materials. Now I think it is developed. They are developing this, but at least a couple of years ago they could not melt or could not print it properly. So so this is one thing which is not required probably. But then earlier, these companies actually, they did not allow the powders from other vendors also, but now they are allowing. But what is the advantage of the SLM material, SLM technique is that it has increasing material flexibility, although it doesn't have that much flexibility as DED. But then aluminum alloy can be melted, copper can be melted, and then aluminum alloy can be melted, copper can be melted, and also, which I have kept in the next slide. So I think the complexity of the products. So complexity, some of the products, like this is a kind of porous structure that can be very difficult with DED. The powder bed, it is easy because it, why it is easy. Let's say this kind of structure also, maybe DED may have some difficulty. So what will happen is, suppose, let's say if you are you need to make a inclined this kind of rods, let's say inclined, let's say cross sign inclined, and then you are building in this direction, you are printing in this direction, then probably your SLM powder bed is a better process, because you have the powder in all the places. So then probably it will have good support. Otherwise in DED it is difficult. So I know, but anyways, we are not going into that much technical here, but you should understand that SLM is a better technique for complexity of the parts, and DED has more material flexibility, although it cannot it has difficulty in aluminum and copper. But anyways, we are not going to all this. I already told you the porosity is higher, which is not desired. If you have pores inside, small pores, small white spaces, so that is not good. This is not good. So here I think the porosity is less, but that means density is higher. The cellular structure, which is actually the metamaterials I told, that is can be done only with SLM, which is powder bed. I will write bed here so that you understand. And this is the nozzle one. This is the nozzle. So yeah, other things are not very important, I think. That will we can and also I think this wall thickness may be important. One is called layer thickness, one is called wall thickness. What does this mean is, suppose you are making a, let's take an analogy of the making a wall. If you were the height of the brick, let's say, is your layer thickness. Just like you are making the wall by putting one by one bricks. Similarly, your the laser scanning will be done layer by layer. So that is the layer thickness. You see, the layer thickness is smaller in SLM. Similarly, minimum wall thickness is nothing but that the feature thickness we can make, like how much the thickness of the wall. Can you make a smaller wall? So yes, here we can make a smaller wall, which is better. Then we can get smaller complicated structure. So this is another technique, electron beam. We are not much interested in it now. So this is also used electron beam, which also use kind of powder bed. But there are. I just want to tell you few things. There are the big table. Sorry, I did not remove all of them. But the scan speed is very fast in electron beam melting. That's why the selective laser melting, the powder bed, selective laser melting is the laser. Here we have the electron, but this machine is very costly. Electron beam melting is, I think, very costly. In maybe SLM, what we got is, let's say, 4 crore or something like that, 3 to 4 crores rupees. And then I think electron beam melting should be costlier. I'm not so very sure, but it will be costly. It should be, I think, more than 10 crores, or maybe it can be even 20 crores also. I don't know the right now what is the price, but yeah, it should be costlier. So the scan speed is very fast. That means you can make a part very fast. But the problem here is energy cost is also good, but the surface finish is not as good as SLM. And then feature resolution, how much small feature you can make is also better in SLM. Then materials also, with SLM you can not only actually metal, there are different techniques which can actually melt melt ceramics, and also we can do polymers, but here you need conducting metals. So, and anyways, we are not going into other parameters. So also, just to show you, don't need to think much. These are the grains we call metallic materials. The mechanical people know probably. The mechanical students, if you are mechanical students here, so you have studied in material science, or even some of you might have studied in school also. I don't know, the crystals, we call crystals. So we most of the metallic materials are polycrystalline. There are a lot of grains in there, thousands of grains in there. So these grain structures are different in SLM, the laser powder bed, and the other electron powder bed, they are different. So basically they may have less porosity, and they have the grain pattern is like a cast structure, like casting. So basically you don't need to go into details, but the grain structure is different, then the mechanical properties will be very different. So that we need to understand, and the porosity is less here. That is the advantage of electron beam melting. So again, we are coming to this, the history of this. So history is like the selective laser melting is, it was developed in Germany, Fraunhofer Institute of Laser Technology in 1995. And then DED is in Sandia National Lab, US. And then commercialized by Optomec, company. Then 1997, they have the first machine. And then EBM, which is in 2001, that is in Sweden. That's a Chalmers University of Technology. But then EOS is a company which is very very well known. They have made this in 2004. And then the other kind of, this is mostly SLM companies. I will show you. These are the companies. I just want to tell you, I mean, this is not required for this presentation, but most of the companies, I think, these are, I think, from German companies. This may be from US, and then Concept Laser or Real Laser may also, I forgot exactly, but this is from UK. And then this, I think, DED companies are, DMG makes even both DED and SLM. But then we have a DMG Mori machine. Sorry, not here. DMG Mori machine, SLM machine, which is also a good company. But then Optomec and other companies are from Americans. Like especially the SLM machines are, as the SLM technique also developed in Germany. So they're good companies are from Germany. But then so coming to the second part. So first part, as I told, in mechanical 3D printing, I'm not that an expert, but we are interested to learn because we got the printer just 1 year ago, although in February last year, but still it had not installed. But we want to study the metallurgy of it. I will again show you a couple of slides on the metallurgy. Metallurgy means how the grain structures are, how that can influence the mechanical properties. Why it is important, I will tell you later, because this is still underdeveloped. This making metallic parts with 3D printing is not a very doesn't have very promising properties yet, because it is difficult to control the microstructure, control the metallurgy of it. So this is the topic I am interested in. Most of my students are working in it. So this is nothing but we also call metamaterials are not only mechanical metamaterials, it can be optical metamaterials also. If you go to even physics department, or even if you go to electrical department, even chemical, they have optical metamaterials, electrochemical kind of metamaterials, or they may have a material with negative refractive index. Like here in mechanical, we have negative Poisson's ratio. Some of you know what is Poisson's ratio. I will tell you. So we can make a material with negative Poisson's ratio with these kind of materials. Generally, it is a positive Poisson's ratio in most of the solid material. So the metamaterials are the materials, man-made materials, that is like beyond the capacity of the behavior is beyond this natural materials. So we can make materials which has mechanical properties. In this case, is very different, extraordinary than the natural materials or whatever existing material we are using. So this is generally, we also call the lattice structure, and also generally we use the word micro lattice because the lattice structures have sub-millimeter rods. It is made of sub-millimeter rods. Sub-millimeter means, let's say 1000 micron is 1 millimeter. We make rods of let's say 700 micron, 500 micron, that means 0.7 millimeter or so. That's why we call it a micro lattice. There are nano lattices as well. In very few places, people are working on nano lattice structures also. The very pioneers are some of the big institutes like Caltech, even Harvard, Delft, and these people are working on that. So I'm keeping this, picture from Kaziranga National Park. Some of you heard about it. Kaziranga National Park is in Assam, which is very close to my hometown. So this is the place, like your the Gir National Park. I don't know how you pronounce it. Gir National Park in Gujarat. So where you get the, I think, most of our Asiatic lions, yeah, all the lions. I think. But here in Kaziranga National Park, we have the world's 3/4 of the one-horned rhinos are in this national park. So it is very close to my hometown. I always cross this national park when I go home from Guwahati. So why I kept this? These are some trees which is we call azar tree. I think this is in Hindi they call jarul or something. And in this is the scientific name Legarstromia specicos and I think specios. And then also, I think some places they call it a pride of India. So these are the trees very common in Assam, and I have seen in my village, the father's village. So, but I have seen that these trees are not used much in our furnitures. That is interesting. These are very commonly available, wood, but that is not used in furnitures in home. So I was wondering, and then I was told at that time that this has a good quality, it has good quality, but it is comparatively heavier than some other woods. So that is one difficulty. So now, but at that time I did not know about the interesting microstructures of wood. But now, very recently, I have gone through these kind of literature. Especially these are from these are from MIT. Although this is the first author, but the main professor, I should write her name, Lorna Gibson, there's a lady professor at MIT. So she's you can, if you are interested to know about the wood structures and these cellular materials, she is the expert, and you can see videos on YouTube also. So so what they see, with microscope, this is very interesting. We actually don't know the interesting structures. I don't know how many of you have seen these kind of structures. About maybe the vessels. You know that there are vessels inside wood. But then these vessels, if you go to small, if you take not these big vessels, if you go to small, this one, it's a cross section. You know what is cross section, right? This is longitudinal view. So if you cut a cross section, the wood, so then you will get this kind. And then if you see from outside, you will see like this, or it's a longitudinal view. In the from vertical, vertically the tree will grow like this, right? This is the vertical view. So so what is happening is, what is interesting here is, when you see a small of these pores. So if you see in a bigger, this is 20 micron. You see this is kind of almost hexagonal kind of shape, and this is empty. This is empty, this kind of a pipe. If you see here, these are the pipes, and if you see on the cross-sectional view, you will see a hollow space. And then this is mostly made of cellulose, hemicellulose, and the lignin. So I don't know much about this chemistry, but this is why it is very important, because it has a porous structure. It has a porous structure. So what happened when in materials course, I also taught a materials course here to BTech, but generally we don't speak about wood. We generally talk about, in mechanical engineers, we generally talk about metals and alloys. Why we talk about metals and alloys? Because the atoms are very nicely mixed, nicely arranged, very densely arranged. So that's why it is very heavy, but it is very strong, or it is very stiff. But generally for wood, we only tell students only maybe one sentence that, okay, wood is a natural composite materials. But there are many important things we should learn from these structures, of these microstructures of wood. So see, this is actually a balsa wood. I think in India also we get this kind of wood, but this is common in North America, US and Canada. So this is one of the most, probably the lightest wood. If you see the density is very very low. It is 60, as you some of you can understand, right? What is for aluminum? What is the aluminum? Aluminum is a light metal, right? So aluminum, what is the density of aluminum? Density of aluminum is 2,700 kg per meter cube, right? Or if you talk about the steel or iron, this will be, let's say, 7,800 kg per meter cube. So if you take a 1 meter cube of iron, 1 meter cube, just 1 meter, you just believe me, like 3 meter, 3 feet, little more than 3 feet, 3 feet by 3 feet by 3 feet. This will be 8 tons. It will be like two Indian elephant, or more than 2, I think. Maybe Indian elephants are even less than 4 tons. So it is so heavy. But the wood you see, this is even, it can be as low as 60 kg per meter cube or 380 kg per meter. Even if you, in our northwestern part, we have a lot of bamboos. Bamboos are also very, lightweight material. So it is very important. See, it can take, load that we call the strength, strength to weight ratio, or stiffness to weight ratio is very good. So as you can see, relative density means how much is filled with material, how much is air. So if it is 25%, means 75% is filled with, like empty spaces. Okay. So so now I want to tell you, for alloys, let's say alloys, the metallic materials, like steel is an alloy, aluminum alloy. So what is the what is the factors that decide the mechanical properties? What are the factors that decide the mechanical properties, or even other properties? So mostly the properties of the constituent elements. When you make aluminum alloy, 95% is aluminum, 4% is, the composition is 4% is this copper, 1% is, let's say, lithium, or maybe 0.5% is magnesium. So this composition, and also the properties of these constituents, like whether aluminum or copper or whatever, and how you process it, how you heat and cool it. Then again you do post processing, that is called heat treatment. So those are important. But then if you talk about composite material, what is important, you might know that composite materials are like, you put fibers or particles inside, let's say in a polymer matrix, we call the matrix outside is, and then you put some fibers, or you put some carbon fiber or something, that is now have a better property. So these constituents properties, and then how much volume fractions of fiber or particles you are putting, and then those shape, size, and distribution of the reinforcement. That means whether it is a shape is fiber or particle, reinforcement means whatever you are adding it to it. So, and then the fabrication process. But now we are coming to woods. So what factors decides the mechanical properties? The cell topology. I think I did not tell you, but what is cell, right? These I'm going back again. So this is, we can call it is one cell. So that's why you call their cellular structures. The cellular comes from, cellular structures come from this kind of cells, and even the mechanical metamaterials we are talking also a kind of cellular structures. So yeah, so this woods, you see how the cell topology is, how the shape of the shape is, and then how much of cellulose, how much of hemicellulose, and how much of lignin is there, and then what is the crystallinity? I mean, some of you know probably the crystallinity and amorphous material. How crystalline is that cellulose? I'm not an expert on that, but anyways, so that is also important. And then how much porosity is there? As I told, 25% relative density means 75% porosity. Higher the porosity is, lower the strength, but it will be lighter, right? And also the microfibril angle. I have shown you that is also very important. How much this, the fibers are having angle with the vertical, let's say, in a growing direction. That is very important. So these are very important. Now, why I am talking about wood, also not only wood, even okay, I'll let you know why I'm talking about these structures. But then honeycomb is also another nature material, and this is a human bone. This is, as you know, this hip bone, like where the femoral head, and this is the hip joint actually. Hip joint. You have a, for joint actually you will have this kind of structures. It will be inside this. So this is also a cellular or porous structure. You have pores inside it. Here the honeycomb is very interesting. I think in 20 years ago, one mathematician proved that is called honeycomb conjecture. I think he has, proved, earlier people could not prove it, that if you have an area and then you want to divide this area with some spaces, then if you make a hexagon, then your perimeter, like this perimeter will be the lowest. If you make a square or something, it will not be lowest. But this honeybees knows this from millions of years. That is the best structure they can make, because the perimeter will be less. They will need to work less, and then make some good structure. But the mathematician proved that I think 20 years ago. They knew it from millions of years ago. And also these the bone structure, the outside is called cortical bone and the inside is called trabecular, or there is another name, cancellous bone. So this is also very interesting. There is some maybe soft material inside these the porous structures. But these porous structures, porous means you have pores, whether it's honeycomb, whether it is wood, or whether it is bone, or even other natural things. You can see even in human body also there are, apart from bone, also other structures also. Maybe you see cellular structure. So these are very important. But we humankind, I mean our scientists and engineers very recently are trying to understand this structure, and the materials engineers try to mimic the structures, try to make structures, may not be exactly the same kind of structures, but trying to employ these advantages of porous structures. So some of the structures people made are metal forms, like honeycomb structures. They make this kind of structures. There are different kind of techniques and mesh kind of structures, but this may not require a 3D printing. So when 3D printing comes, this is, as you know, 3D printing is very new technique. So people have made this kind of lattice structure. This is the structure actually metamaterial we talk about. These are lattice structures we call. Lattice is a word. As you know, this is not actually only in material science, but this is actually a mathematics. It comes from mathematics. I'm sure even computer science people also probably know this. So it comes from mathematics. So if you have if you repeat some points at the regular intervals, that can be called a lattice, right? So that can be called a lattice. But when we talked about atoms in it, let's say you put atoms in all the points, the point definition is from mathematics. But if you put atoms in here, then it is a crystal lattice, right? Then it is a crystal lattice. So we call crystal lattice structure, right? So then crystal is, the atoms are at angstrom level, 10 to the power minus 10, which are actually the every material made of this. And then when you talk about metallic material or some ceramic or even some polymers, we call crystalline material, which are nicely arranged, which are very densely packed. So them only we call them lattice structure, because that is a periodic. What is the distance here is equal to distance that side is equal to distance that side, or maybe equal to this distance is equal to this distance, right? That's why we call them lattice. Otherwise, amorphous material, which are not crystalline, they are not a lattice, because the atoms are randomly arranged. There is no kind of this kind of pattern. But now, I'm sure all of you have studied nowadays. We did not study in our school, but you have studied in 11th, 12th standard, the FCC, BCC. These are in atomic lattice structures. I mean, sorry, we can call crystal lattice structures. But now people have mimicked, people inspired from those crystal lattices, they make some structures like this. These are rods, we call struts. The rods are called struts, S-T-R-U-T. Generally, we call them struts. And struts, the design can be like BCC, or that can be, I have shown even in the next slide, BCCZ, FCC, some different kind of rhombic, gyroid, F2 BCC. So you don't confuse with crystal or whatever you have learned. It is inspired from them, but this is not FCC, BCC kind of crystal structures. These are, you can see this is a paper clip, right? So you can see how small this is. Even I have here with me, I have these structures. I could have shown him, but anyway, you have seen that. So this is one that they call, this is ultra light microlattice made by Boeing, that or aeroplane making company. So this flower is called very common flower, right? This is called, I don't know if it's found in India or not. That is called dandelion or something, dandelion. So they are showing that this is so light. They have made very light. We could not. I mean, we also, my students also made something that is not that light, because they have their they have better technologies, and they have made this. I think one of them, I think this kind of structures made even 10 years ago. One is polymer, then metal one, they made it in 2015. They're saying that they're the lightest material. Why they put on the flower? Because the flower is very light kind of flower, right? And then it can even bear the weight of that lattice. So, so what is the advantage of these lattice structures? As you can understand, they are very, very light. they may not carry that kind of load like a solid structure, but the strength to weight ratio, strength to weight ratio, or stiffness, we call stiffness, that is sometimes we call Young's modulus, right? Some of you know Young's modulus. Stiffness is actually elastic modulus is a indication of that is the same as like stiffness, you can think. So strength to weight ratio or stiffness to weight ratio is very good in these materials. So now again, we will show different kind of structures. People have came up with different kind of structures. It is cubic. These are all not crystal structures. These are all people want to make some structures, materials which are very light. But then if you change these different kind of unit cells, we call these are unit cells because this is the building blocks. Like you make a wall with hundreds of bricks. So the same kind of, this is let's say one brick, and then you put bricks on top of each other, one brick on top of each other, and then you can make a entire the lattice. The lattice is actually the entire thing, and then the one building block we call is a unit cell, which can be repeated to form the entire lattice. Even there are some surface based also. These are rod kind of, as I told, this is strut based, strut based. Oh, sorry, it is written here strut based, but these are rods. And then there are the others are these are the surface, not kind of rod. It's like a plate or maybe curved plates. So this is my office. It is me holding that some crystal structure. These are the models for crystal structures made by our BTech students. But generally, the real crystal structures will at angstrom level can be seen like like this, because these are the atoms and they are very closely packed. But now, as you can see, these we put these sticks, that is called ball and stick model. Ball is these atoms, but it is not a correct structure. Actually, this is a correct structure. That should be very, the atoms should be close enough. But okay, we make these kind of structures to it is easy to understand. But this is just to show you, this is the crystal structure is the inspiration for all of us to make this metamaterials. So now I will show this. So I think yeah, I have already maybe taken probably around 40 minutes. Yeah, so we have, okay, let's see. So this is oh, I did not written that. This is called SB plot. Generally, SB is the person who popularized this plot, SB's plot. So this is two of them. One is Young's modulus. I told Young's modulus. I think many of you know that, right? When you I think, I don't know, maybe you have, some of you have learned these things in your 11th, 12th, right? I think even the computer science, other students also, when you draw stress strain curve, we call stress strain curve, how much load it can take, and this side we have strain, how much deformation will happen. We have a stress is we call sigma. So then we have the stress strain curve, and the stress strain curve, the slope of this curve is the Young's modulus. That is the measure of the stiffness, how stiff it is. And then the other plot is, this is strength, how strong it is. This is strength. We write sigma f or failure strength. And the other, this side it is density. As you can see, kg per meter cube. Density here is also, it is density. So what I want to show you, if you talk about metals, in this case, let's say Young's modulus, the metal is like this. It has high Young's modulus. It has high Young's modulus, but it has high density as well, right? Like I told you for steel, it is 7,800. So like it will be somewhere like this, right? 7,800. This is a log scale, right? The 10, 100, 1,000, and 10,000. So 8,000 kg per meter cube. So that is, and for aluminum it will be less, but then again it will be somewhere here, 2,700. But then we talk about these natural materials. Some of the natural materials like wood or something, it will come like this. And then foam structures. I have shown you foam structures, which is kind of also a cellular but irregular shape material. And then, as I told, the lattice structures, which we call the metamaterial. So this lattice structures, the aluminum lattice look like this. It has a good range, even composite lattice also you can make. So what is the beauty of these structures are, it has low strength, as you can see, low stiffness, but here this density will also be very less, very less. So similarly, even for strength also, if you see aluminum lattice, it can goes higher also, because why it is higher? Because you can control the porosity, how much pores you want to put, like whether you want a 25% porosity or 75% porosity, depending on that, it will increase or decrease. But then, although strength is low here, but the density is also very low. So that is important. Very lightweight structure. Suppose for aeroplanes, we need very lightweight structure. But some of the potential applications, see, you must be wondering, because these type of materials you have not seen it yet, right? Yes, it is actually very difficult to convince you, but this type of materials, this mechanical metamaterials has very less use now because of the cost of 3D printing process, and also probably, you know, other thing is the materials, especially for metallic materials, it cannot achieve very good property, like especially mechanical property. So this kind of helmets actually exist. You can make these lattice structures, can be used, whether it is polymer or sometimes you can use metal here for ballistic or blast resistance vehicle. So what will happen is, why we don't want to put a solid metal here and then put this kind of lattice structure. Lattice structure is something like this, there will be pores inside. Why we want to do this? Because it can absorb a lot of energy. Why it can absorb a lot of energy, I will show you again. There are other pictures and plots, but it is lightweight and it can absorb a lot of energy. When you have blast heating, or let's say vehicle crash, vehicle crash also, it has you can, if you employ this, if you apply this lattice structure, then it can absorb a lot of energy. So people actually use foam. Foam is easier to make. Foam is cost is less. That's why people use foam in some of the structures, but not 3D printed structures, because it is very costly now. So similarly, the potential applications, as you know, these yellow parts are the lightweight aeroplane body parts. You can, some of the actually probably Boeing company, and they have probably used some of these lattice structures in some parts of the planes, but it is not very well known which parts they actually make. But you should understand, you should realize that why Boeing is doing that kind of research, right? I have shown you that very lightweight lattice they made. They have very good technology that is funded by Boeing in a US lab. So basically, this kind of materials have a lot of potential, but only problem is now it is costly. And some of the aeroplane parts, actually, they have probably, in some planes, actually, some aeroplanes, at least they were using this kind of materials. But in future, surely in a lot of parts in aeroplanes, because we need a lighter structure for, especially for fuel economy. So, and also sometimes for, let's say for energy absorbing capacity, like let's say bird hit. I mean, two planes, if they collide to each other, like probably then it will be very difficult for any kind of material to withstand that here, collision. But let's say, some kind of light hit, like let's say hitting, when it hits a bird, then you need to have a good kind of material that can absorb energy. Absorbing energy means it doesn't transmit to the other part of the material. Like when a car crash, the frontal part should absorb the energies. It should not transmit to the the main part where the passengers will be sitting, right? So that kind of structures are required even for aeroplanes, for light hits. And then this part, let's say high-speed train from Germany, so they use metal foams. I want to go back. What is foams? I'll tell you. This is actually metal foams. That is easier to. There are some techniques that is easier to fabricate than the 3D printing, right? So what is happening here is, as I told, in these kind of trains, actually they use metal foams, but yet micro-lattice has not been used, or micro-lattice or lattice, whatever you call. Micro-lattice are smaller ones, smaller rods, and similarly for this is honeycomb structures they are using, which is also basic. Honeycomb structures, foam structures, these are kind of little basic structures which are the same metamaterials, but they are not 3D printed and hence they are less costly. But if you can make 3D printed lattices, then probably you have more control over it. You can have any kind of lattices, FCC, BCC, or whatever. So then you can have better control over the properties. So here I think vehicle crash box, right? Vehicle crash box you can make with this kind of materials, and especially anti-injury wares. I have shown you about the helmets, right? And high-speed trains, even defense applications you can use in, as I have shown, in blast resistant vehicles, or even you can use this in your it is possible even to use in the bulletproof jacket also, but you need to make a very kind of thin lattice that may not be possible with some kind of printer. So I just want to, this is two different types of lattices. The 2D view you can see here. The one is called stretching dominated. It is before deformation, and then when you are deforming, what you are doing is you are compressing it. Then you see this is damaged, like kind of compressed. So this is stretching dominated. So if you draw the stress strain curve, I have shown you, right? If you draw a stress strain curve of a solid material, not a micro lattice material, then your stress strain curve generally goes like this straight line, the elastic portion, and it goes like something like this, engineering stress strain curve. But in this case, that is the difference. Why it can absorb a lot of energy. It goes like this, but then it goes flat. It is called plateau region. Here also, this is for this kind of lattices, and this is for this kind of lattices. So there is some difference, but it will go, still it is going flat, right? It is not going up like the solid material, right? So that's why what will happen is it can absorb a lot of energy. So energy is like, how much energy is generally, some of you know, mechanical students, that is the area below the stress strain curve. That area is quite high than actually solid materials. Solid materials, what will happen is probably this will have higher strength, but that strain may not be that high. So that is, the area will be less. Here in this case, we will have higher area. So this toughness, you can use the word toughness, or we use the word energy absorption is high. That's why for crash resistant vehicle, for crash resistant maybe aeroplanes or blast resistance vehicle, so you can use these kind. But only problem is now the cost is very high because of the 3D printing processes. So we are not going into bending dominated and stretching dominated. Their mechanics is a little bit different. We don't have slides to show you, but anyways, this is one slide. This is called FCC, inspired from the FCC crystal structure. This is called BCC, and when you put vertical struts, which is called BCC-Z in the Z direction, and then when you put Z direction strut in FCC, it is called FCC-Z. So you can understand here the solid BCC is this curve, stress strain curve. These are stress. This is stress is the load, how much load it can take, let's say, divided by the area, right? And then here the strain. This is in just give me a second. This is in percentage, right? So like what is the how much the compression will happen. Let's say you have the lattice something like this, and you were compressed. It is compression only. This is how much compressed. Let's say 20% compressed. That means the lattice will be something like this. That 20% is got compressed, right? So that is the or we generally get the load displacement curve, load on the y-axis and displacement in the x-axis. When you do we use UTM, right? Generally we use UTM, universal testing machine. Some of you know that. So that machine, we compress the material and get the stress strain curve. So FCC-Z is here, and FCC is somewhere here, and BCC is somewhere here. So that means these mechanisms are different, as I told, bending dominated and stretching dominated. So just to show you, we are not going into details of these mechanics. So so this is two different kind of structures where you will get two different kinds of kind of stress strain curve. Stress strain curve is very important because stress strain, depending on the stress strain curve, from the stress strain curve, you can tell what is the strength, what is the stiffness also. What is the slope of this curve. Somewhere here you can get the stiffness. So what is the stiffness? What is the strength? How much strength it has? And strength is, yeah, what is the stress it can take actually. So strength, stiffness, and also the energy absorption, entire, all these things we can get it from these kind of curves. Again, there are some mathematical equations also. Again, the Gibson, I told SP Gibson models. So we are not going into details of that. They have made some very simple equations. So what they did is they are saying that rho S is the density of the solid material and rho star is the relative density of the material. So we are not going to discuss how much is porous. Depending on that, you will get the rho star. But then that will give you, that will give you the the predictions where these bending dominated structures. Bending dominated is one class of structure. I have shown you the different kind of BCC, FCC, where this is density versus relative strength or relative modulus. The modulus means is Young's modulus of stiffness. So this is just to show the these equations. Some researchers come up with some equations, and that can give actually quite good prediction where these points will lie, where the strength relative to density or where the stiffness or modulus relative to density will lie. They can actually tell, irrespective of the structures. But anyways, but some structures, let's say BCC is better than FCC. So that's why we do research to get a good design of that unit cell. So that is very important. And still people are doing research to get better and better unit cells, to get better and better mechanical properties. So this is another important property which is interesting. I have told you about strength, I have told you about stiffness, I have told you about energy absorption, but this is called Poisson's ratio. Some of you know that the Poisson's ratio is the ratio of the lateral deformation by longitudinal deformation. So what will happen, this kind of a lattice, when you deform it, let's say you are deforming, it means you are compressing. Let's say you are compressing it 0% compression, the 10%. Let's say this is, let's say 10 centimeter long, or maybe, or you can call 1 centimeter also, because we make very small structures. Let's say it is 1 centimeter only. 10% deformation means now it is 0.9 centimeter from here to here, right? So then it is 20% deformation. 30% deformation, 40% deformation, 50% deformation. What is the beauty of this is it has negative Poisson's ratio. I'll write NPR, negative Poisson's ratio. So when you take a solid material, if you take a solid material and let's say this is a square, let's assume this is a square, and when you try to compress it, let's say compress from both sides, or let's say this is fixed, you try to compress it, what will happen is this will be something like this. So the final structure is something like this. It will be the height will be reduced, but it will expand. But in this case, that is the lateral deformation, right? The lateral deformation. How much is the lateral deformation divided by your longitudinal deformation? But here in this case, the Poisson's ratio is negative. That means the lateral expansion is not happening. If you see, when you are deforming, sorry, this is creating a problem a little bit. Okay, so when you are deforming. When you are deforming, this is actually going inside. It should going outward, but it's going inside. So design is like that. So this is one called re-entrant kind of lattice, not like FCC, BCC. So this is, by the way, if you deform more, it will go out. Only in the beginning it will go. It will shrink in the lateral direction, but maybe after some time it will go. It will expand. But anyways, till some point of the deformation, it will go inside, because when you are compressing from the vertical direction, the horizontal direction should expand, but it is going inside. So that can be sometimes very useful. And also the indentation resistance, when you hit with a, let's say, kind of a indent with a, let's say, cylindrical kind of projectile, or let's say bullet impact, that can, I think, it has a better property than the other kind of lattices. Another thing is this is they make functionally graded. If you see here, it is increasing. This way it is increasing, thicker. The struts are thicker, rods are thicker. So these rods are thicker. So we can control this, like which layer, when you deform the material, which layer will deform first. Let's say first this will collapse, and then second this will collapse, third this will collapse. So we are controlling it so that if you see, when you make it is called graded or functionally graded. So graded structure has a something like this, and that when it is not graded, that means the struts are uniform shape. So then it will you will get it like this. So that may help us to get sometimes, let's say, more energy absorption. In this case it may not be, but sometimes we can get more energy absorption also. And then I did not tell you probably in the previous slides, but at the last portion we call densification. At this point we call densification. Then what will happen? The struts will come close to each other. It will like a solid material. Now, initially there are pores inside. When you are compressing it, at last the strut will touch each other. That will that will probably make the material more like a solid material. That's why the strength will increase. But then the energy absorption, how much energy it will absorb, we generally calculate only this part, not after that part. So there are different kind of lattice structures people have made, very different kind of structures, very complex structures they make. They put inside FCC, BCC all together. These are people from very top, places like Sandia National Lab, which are one of the top US lab, and then even I think Los Alamos, or even in UC Berkeley, University of California, Berkeley. So, so what we do now, I will show you at last. I will show you some our research. There are a lot of slides. Anyways, I will skip. Don't mind. The one area is we work on high entropy alloys, which is a very special kind of alloy. If you are interested, please study that. That is very new class of alloy. It's a very good future prospect. And then we do 3D microlattice, which is I call as a metamaterial. And then we are now working on metallurgy of 3D printing, and these are actually called connected. But anyways, these are the structures we have made. This is metal. This is also metal. These are polymers we have made. Although if you see from close view, these are rough. The metal. It is a metal, not steel. Aluminum, ALSI 10 Mg. So aluminum is mostly 10% silicon, and magnesium is less. So that kind of material. This is a little brittle. So why we call microlattice? Let's say this is 700 micron or 0.7 mm diameter rods we use. Generally, this kind of materials we use, or sometimes even 0.5 mm. So that's why it's small. We call microlattice. So these are, you make computer model, and then you give it to computer model to the printers. They can print. We made this metal lattice outside and outsourced it to some company because our printer is still not working. So I will show you just a video maybe for the metal lattice, how we get the stress strain curve. These are the stress strain curve we got. One of my PhD student Akshay has done that. But this is a little brittle, so it break like this. It break like this, when you compressed with a UTM, universal testing machine. But this is a polymer. This is more ductile. It's a PA12 polymer. PA12. This is a nylon. And then I just want to show you. Don't need to bother about all those stress strain curve. But this finite element method, we use finite element method FEM to do the simulation. And then see, this is experimental. This is the real one from experimental. So they are looking same. So finite element gives a very good prediction. When you do first, we do finite element simulation whether this structure will be good or not. Then we go for experiments. So this again. I will just want to show you again the video. See how nicely it's goes inside, like like compressed. So that's why it can absorb a lot of energy. Although it's a light structure, so what will happen if you take a solid structure? It will kind of directly break or something, but it is without complete failure. If you put it under, let's say, a front bumper of a vehicle, so it will absorb the energy, before transmitting, a lot of energy to the other passengers. So that can be possible. So it is another my PhD student Vikram, and he did another interesting thing. We are going to submit this work also, like other work we already almost accepted. So this is for the first time we have done this. The Poisson's ratio we used we call rule of mixture, which is used for composite material. So now we have used the positive Poisson's ratio and negative Poisson's ratio material, and we just predicted that, okay, if you put 42% of this, then you will get a 0 Poisson's ratio. Nobody has done that. So although it is looks obvious, but then this is very interesting. With the help of this, my student got a 0 Poisson's ratio. What is the 0 Poisson's ratio? When you compress the material, it will neither expand nor contract, shrink in the lateral direction. So this kind of lattice structure he made, but then the earlier lattice structures, these are existing in the previous literature. Somebody else done it from other, maybe from US or maybe from Europe, China. So these are the structures people have made. These are very interesting structures, very complicated structures. But what we did is we made the structure. Our unit cells are not different. We got it from literature, but we mixed it together. So what will happen? So we got some better results than them. So suppose our structures are PRC and FRC, these two curve, and then the somebody else did SRE. So their curve is low. That means their energy is absorption is low, but we get a higher absorption at the same relative density. That means our structure has same weight, and we have the zero Poisson's ratio. We call ZPR. We have the zero Poisson's ratio. They have also zero Poisson's ratio, but our structures are better because what we do is we mix it together. We call it a composite. Actually, we inspired from composite. We nobody has done with respect to Poisson's ratio. Some one or two papers are there in for Young's modulus. We mix it together. We can now predict that mixing together will give us a better result. Actually, that is also we good to. I want to say that we have actually get the Poisson's ratio till zero Poisson's ratio till 6% strain. So when you 6% compress, till that point it will be zero Poisson's ratio, which is I think a good achievement. So, but other structures, if you see, other structures are not doing that well. Although this RSRE is doing well, but here is energy absorption is less. But anyways, the another work, my another PhD student is working. So, which is a plate structure. We are putting a plate structure with start lattice. This is plate structure. This is the start lattice are the most common lattices. But then we realize the plates are with the same relative density. That means with same weight. If you take two, one is plate and one is start lattice, and then the plate lattice will have higher strength and stiffness. But the problem with the plate lattice, if you make this kind of lattice, if you repeat these lattices, if you repeat, 10 unit cell this side, 10 unit cell other side, X side, Y side, and Z side, then you make a bigger lattice. But the problem here is this is a powder bed method, right? So the powder will be inside. Then the powder will be entrapped inside. You cannot get the powder out of these plates. That is the problem, right? If you put these plates together, there will be empty spaces, but there is no holes. But the people have made some holes also. Some researchers done some with holes, but still we have come up with a new technique. So what is happening is that this is not a very kind of rocket science, but we have just mixed it. But nobody has done that. We have seen that. So you put some of the lattices are strut lattice, some of the lattices are plate lattice. So now he has got actually some good results with this. Now powders also will not be entrapped inside, and then we are getting a reasonably good mechanical properties like strength, stiffness. So this is another my student who is starting this work in biomedical field. So if you see that the total hip replacement, which is very important nowadays, but there are many people even die because of the hip fracture or this kind of especially old people. But the problem here is the estimated lifespan of these implants are 15 to 25 years. It may be even 10 years. So what will happen if suppose a young patient, let's say if it's a 40 years patient, have some hip fracture, then this will last even only, let's say 10, 15 years, it may not be 25 years. So at the age of 50 or 55, again, he need to go re-surgery. So people are trying some kind of different kind of implants. So these are commonly used, cemented and the porous, they call porous coated. What will happen is the implant will be like this implant, and then some coating will be there. Only this portion, there will be some pores so that the outside bone material stick to it. But then people are doing now research, some of the European universities doing, and we are also started that. So that can be fully porous, so you can see through it. I mean, like this same microlithis, we are putting it here. So we have actually the preliminary stage of this, but it has actually several advantages. We don't have time to discuss it, but it has several advantages. But there are limitations as well, because it may not have a good fatigue strength. But it has, if people can make it, it is not yet used. Although people have done research in Europe or other countries even, but it is not yet used. But I think I'm sure that in 5-10 years they will be successful to use it. And then the bone, especially for young person, not for 80 years old. So you may get bone ingrowth. The bone will go inside these lattices, and then that may reduce the failure, and that may actually extend the lifetime of this implant. And then we are starting this metallurgy work by my PhD student by Mr. Hitavan. So that is also interesting. I'm not going to discuss because we do not have time, but you should understand that engineering the alloy microstructure is very important. So still it is in the development stage. We need to control the porosity, less pores inside, the grain morphology, which is important. That these are the grains, actually different colors. If you see, these are the grains. These are elongated grains. That's why these materials do not have good fatigue properties. When you do cyclic loading, thousands times, if you put it in a car and then you have 1,000 times of cycles, then it will fail actually, because of the grain structures are not good. You need to control the grain structure. Then also the surface defects and other things are there that we don't need it now. These are a little advanced. So we want to play with these things, because still research are going on. Why we are not getting good metallic structures in 3D printing? Because we have not been able to get good microstructures. Still researchers are doing research on that. Maybe it will take maybe 10-20 years to get very good mechanical properties. Still people are trying hard to change the metallurgy. And just I want to show you maybe fatigue strength we are trying to understand with density. So a different kind of, as I told, cubic, FCC, BCC, this kind of lattices, but we are studying it. That we have seen that this is, if you divide fatigue strength by the yield strength, so you will get that. So that is very important, because let's say your yield strength is 100 megapascal, or let's say 10 megapascal, but fatigue strength is low. So you don't think that if you put, even if you put in a hip implant, or you don't think that your yield strength is 10 megapascal, let's say, and then the human needs only 10 megapascal bone. But then the fatigue strength, when you walk thousands of times a day, then the fatigue strength, it cannot take 10 megapascal. So that is the problem of these porous implants. Also, people have not been able to do that, because the fatigue strength is low, because of the people have not been able to control these microstructures. And there are we need still, it is in the development stage, metal 3D printing. And then the factors that influence the porosity. If you have more pores, that they say that okay, we have only very less pore. Our material has 99.7% relative density. That means only 0.3% they have porosity. But then what they claim may not be always true. There may be more porosity, maybe 1% porosity is there. So that is the problem. We need to control the laser parameters, the scanning strategy, and then powder, how big or how small, or what kind of powders are. Scanning strategy means how your laser is scanning different, it can scan in different way. So that strategy is also very important. And the future of these lattice structure, there are other small scale nano lattices. As I told, the nano lattices, there are different techniques. Some of the California Institute of Technology, Caltech, or maybe Harvard University, and some other University of California, Los Angeles, or maybe Europe also, some places they are working on nano lattices, which are very small. If you see this, where is this? Yeah, I can show you. This is very, very small. And if you 3 micron, right? 3 micron, here to here it is on 3 micron. So ours is, I told, the one rod is 700 micron or 500 micron. Those are micro lattice. Here they have made this structure with different techniques. These are very different techniques, but they can make these structures. I mean, for nanotechnology, it will be very helpful. It is, and also this. I'm coming to end. I've already took yes. Oh, sorry. I've already took more than an hour, I think. Sorry about that. So the multi-material. I'll finish this with this. The multi-material, microlattice can be. This is the future. So you put, if you need the steel in one part and the other part is maybe the aluminum. So you may be able to do it with the advancement of this rapid advancement of 3D printing. Then multifunctional. You need mechanical metamaterial, or maybe you need some electric thermal. Let's say you want to. There are some thermal metamaterials. If you heat it up, it will not expand, because the structure is like this. It will not expand. So the multifunctional, you put mechanical properties and thermal properties also. Also nanolithics, I already told you in this. And then so what is happening? This is the picture, common picture. That we have teach our BTech students, or even probably in school also you got it. So this is the metal, one kind, ceramic another kind, polymer one kind, and the mixer of it is composite. But now I feel this is, I have made it, not others. The metamaterials comes in everywhere. Like you can make metamaterial, this kind of lattice structures from metals, from ceramics, from polymers, from composites as well. So this is very important. So you can control the structures and get different properties, lightweight structures. If you want ceramic, you do it. If you make it, if you need metal, you make it. But the only problem is now it is very, very costly. But rapid evolution of 3D printing, I'm sure that the cost-effective fabrication of this will happen. So on a positive note, I want to end. Suppose when I was in school in maybe 20 years ago, or so what has happened is one page, when we want to print, one page took actually 10 rupees. Now everybody has a printer at their home. So similarly, as you know, nowadays 3D printer also, people are getting 3D pen, and even in schools, I think kids are getting some 3D printer. So now I think in 10-20 years, so we will get even the metal printers will be less costly, and we'll be able to make metamaterials. I hope in 10-20 years you will get some furnitures, furnitures made of metamaterials, let's say polymer metamaterial like microstructure. So that will be, I think, surely possible, a lightweight furniture, so that you can probably lift your bed like this and you can throw it somewhere else. So that can happen with the advancement of this 3D printing with less costly. And these are my students who actually, they are the one who did this research work. So I have already shown you. They're very enthusiastic people are here from across the country. So this is a Gyan course. Just I want to advertise this from day after tomorrow. So I have already sent a email to Dr. Siddhesar Rotre. I mean, this is a course. This is a very expert professor who has a more than 15 years experience in US Army Research Lab. He will talk about similar topic, but he will talk about how this natural materials are, can be used. Our materials or structures can be designed by mimicking the natural materials. So his lectures will be very good. So I just request you, whoever interested, to join this. And we have only 200 rupees for students, but I think faculty members also can, although it is little more fee, but I think with 200 rupees they can do it. You don't need to, if you are interested, please, I have given the email, you can probably forward it. And then it is written as GAN portal registration. That is not required. GAN portal registration is not required. Only fee 200 rupees to IIT Guwahati, that is required. And you can upload the PDF file, and then you have a Google form. You have a Google form and then you just need to rupees 200 proof of payment. So that's all. Then you will, because if you do register officially, then you will get the certificate also, and also you will get the course material also, whatever slides you will be using. Especially it is very important because this person is very, very experienced. He's like quite senior also, is very experienced. He even worked with my PhD advisor in the US. So he spent his almost all the life in the US. So but anyways, so I'm requesting you, if you are interested, please join us. Thank you so much. So this is our campus. I am sure already sir is saying, I think Professor Dean is saying about this. So this is the campus. If you come in May or June into IIT Guwahati, you will see this is called Serpentine Lake. So I hope I invite all of you after this pandemic situation to visit IIT Guwahati, and for any kind of course or GAN course or whatever, or maybe for internship, or for any other faculty interaction. Already we have a connection between IIT Guwahati and your university. So thank you so much. Thank you. Sorry, I actually took more time, so I could have sorry about that. It is 4 o'clock already. So it is, I think we started before 2:55, although it was 2:55, right? So any kind of queries on that?
Am I audible?
Yes,
Am I audible? Sorry.
Yes,
Okay.
audible.
I'm so sorry, but I would love to say that we would be definitely visiting the campus, as it's so beautiful. And your talk was so capitative that, I didn't want it to end at all. And everyone would be agreeing to it. Talking about the lecture, sir, it was really very enlightening in the field of 3D printing. Also, you gave a very comparative study about SLM, DED, and EBM, especially emphasizing on the wood material, because those images even I never have seen it. So that was a very beautiful way of putting into the slides. So we have few questions from our students. The first question is there a limitation to what shapes you can 3D print? Is there any limitation to it?
Sir, please unmute yourself, sir.
Sorry about that. So yeah, it has limitations. So as I told that the powder nozzle, I think what I understood, because see, I have not used the powder nozzle, but we interact with all these companies. They came here and to give presentation. What I understood is the powder nozzle, it is very difficult to make this kind of lattice structures. And even for the other technique, the powder bed SLM. So what happens is when you make a structure, if you can see my video, I don't know. So so like if you make an inclined structure, there is a issue like you can make, let's say, a strut, that means rod 60 degree to the horizontal, that is probably fine. But if you want to make it 30 degree to the horizontal, still it is difficult. It will not, because although there is a powder, if you see the powder is there is a support, but it is very difficult to make a 30 degree. But then people use, there is another thing called support structure. There are other structures which can be later removed, but for lattice structures that also is difficult to put a different support structure, because there are a lot of links. You cannot put structure. But in polymer printing, I think we can use two material printing. Generally, it is easy with polymer printing. So the support structures are made with a different material, and then you do some chemical treatment or so, then the support structure will go away. The main lattice will be there. So yeah, it mainly the if it is inclined strut or that kind of, or let's say. And another thing is, for if you want to hollow sphere, let's say, like a ball, hollow sphere, that will be difficult with the powder bed. I think the powder nozzle will be a better technique there. So because the powder will be inside, you need to have a hole to go take the powder out from the ball.
Okay. Thank you, sir. Actually, we have a in-house comment, like Dr. Kiran Patruni. He says that it's a very interesting interdisciplinary advanced topic. He's from Biosciences department. So his question is, my question is, to meet the metal 3D printing, what kind of rheological instrumentation can be used to load metal samples?
No, I did not get it. Metal, sorry, can you please repeat it?
Yeah, his question is, what kind of rheological instrumentations can be used to load metal samples?
Rheological, no, I am not very clear about the question. So metal samples, is he online, or maybe if I want to?
Actually, yeah, he's a little sick and he's from Facebook online. So
Okay.
I'll just.
So okay, metal samples, rheological instrumentation for metal samples means, yeah, a little bit. I think, sorry, I can maybe interact with, say, him.
Sure, sir. I would
but metal samples, what I understood is, because if he's saying about lattice structures, and whether he's talking about the lattice structures or directly metal printing, that is a little bit I'm not very sure. Yeah.
Okay. So he
Yeah,
was
so he can
asking about the mechanism, the metal mechanism, how it works. So yeah.
So sorry, metal.
Metal mechanism, the mechanism part, the rheometers.
Sorry, no, he is saying about that.
Yeah, he was no, actually he just asked me the question, sir.
Okay. No, the mechanisms means, if you are asking about this, it's just a we have that solid structures. It's like a it's not a kind of mechanism we use. If you see my hand, like, it's not a kind of that kind of mechanism we use. So we have a solid structures perfectly perfect bonding in there. No kind of other kind of hinge we use it in the metal structure. So only this shape of it, the topology, we change it, like whether this vertical strut will be, let's say, angle 60 degree or 90 degree or whatever angle. So those angles only we play, but otherwise this is not kind of mechanism we learn in mechanical engineering. So I don't know whether that is the query, or I'm not very sure.
Yeah, definitely. He would be contacting you, sir, in detail.
Okay, that will be good. I think
Yeah.
this if he's interested, I think even to collaborate also, because we are also interested in
Collaboration. Yeah.
biomedical. We are not very expert on that, but we have started, so we can write to me. Yeah.
Thank you so much, sir. Now I would like to request Dr. Arun Kumar for concluding remarks. Dr. Arun Kumar.
Thank you very much, sir, for your outstanding presentation. And this is just the learning, and the student gets a lot for this. I am Dr. Arun Kumar, head of the Department Mechanical Engineering in the University, Gujarat. It's my honor and privilege now to give a vote of thanks to all those who helped make this assembly happen. Actually, I have some also discussion. It's a very outstanding topic. I want to just correlate this topic that the 3D printing is just the speed up the technology and technological growth. And just if you think about the age of this Kalighat, it is almost 12 years lifespan only. At present time, its average age is 60 years, but after so many times, the age only become the 12 years. So the fast speed up technology it is required, because in that period only, we require to do a lot of things. Just like relevance from the mythology to Vishwakarma, वो उन्होंने मतलब सोचते ही मतलब वो बिल्डिंग बना दिया करते थे. जस्ट लाइक इन द 3D प्रिंटिंग, हम लोग अब 2D ड्राइंग करेंगे और 3D बन जाएगा. तो वो हम सोचते थे कि कैसे ऐसा हो गया, लेकिन अब वो 3D प्रिंटिंग टेक्नोलॉजी उसको वेरीफाई करेंगे. तो दिस इज द अपलोडिंग फेज. अगर 3D प्रिंटिंग फुल फेज में अगर एप्लीकेबल हो जाएगा, तो फिर वो चीज होना शुरू हो जाएंगे. जो हमारे पास 12 इयर्स का लाइफ स्पैन बचेगा, उसी विद इन दैट पीरियड ऑफ टाइम वी कैन डू अ लॉट ऑफ थिंग्स, और वो सारे लिविंग स्टैंडर्ड हो जाएंगे उसी 12 इयर्स में. So it's a very outstanding topic and the outstanding presentation by Prasenjit Khanikar sir. Now, we would not be here without our school's generosity. So first and the foremost, I'd like to thank the school for giving us the opportunity to gather here. I'd like to thank Dr. G.S. Yadav sir, Vice Chancellor in the Rishil University, for taking time away from their curriculum to allow students to hear this message. I'd like to thank Dr. Amish Vyas sir, Dean School of Engineering, for their time here. And at the same time, I give my respectful obeisance to Dr. Namrata Bajaj ma'am and Dr. Sanjay Garg sir, Pro Vice Chancellor, for their support to organize these events successfully. And also, once again, I want to tell something about Dr. Prasenjit Khanikar sir. Their presentation is outstanding, and this is obviously the students are getting benefited for this. Thank you very much.
Thank you once again, sir, for delivering such a beautiful expert talk. We would love to hear you once again in near future, and would love to collaborate with you. Thank you so much, sir.
Thank you. So, yeah, anything, I think if you have any queries on this, because metamaterials, I mean, I have used the word metamaterials, but it can be used as other words. I did not even tell that this is called lattice structures or microstructures. Even they call architected, word I did not use it, architected materials. So if you are interested to, because printing this in polymer is not very costly. If you are interested to print, and even not for research, maybe to show students, the polymer, you can make it very easily. Metal lattice printing is costly. Even we did outsourcing. But if you are interested, we can help you at least to source to some students. Even I have maybe structures where, if I that I have some structures here with me, but so you can show it to the students, because I feel that this is the future. I mean, we will get this kind of material in near future everywhere, as I told, even in the furniture also. Yeah. Okay, thank you so much.
Certainly, sir, we would love to, I mean, we would love our students to witness all those structures which you are talking about. And definitely from our end, we would be contacting you, sir, on this.
Sure, sure, sure.
Thank
And
you,
then
sir.
internship is very, you are very welcome. Like, let's see if this summer may not be very easy for the pandemic situation. So otherwise, if students are interested, they can come here.
Yeah, sure, sir.
Yes.
Thank you so much.
Thank you, Dr.
Thank
Prasenjit,
you.
for accepting our request and presenting such a beautiful presentation. So, sir, I will be contacting with you for further collaborations of our engineering department, mechanical engineering department with your department at IIT Guwahati. Thank you so much, sir.
Thank you so much.
Thank you,
Thank you so much for inviting.
Thank you.
Thank you, Dr. Prasenjit.
So I'm ending the meeting. Thank you.
Yeah.